Alright friends, hi there, my name is Max Wolf. I'm TA for CS61A in spring 2015, and today I'm going to do a walkthrough for quiz 2. Okay, so I've pulled up the quiz 2 directions, downloaded this quiz2.zip, unpacked it. Okay, great, so I've got an OK file, this quiz 2 OK in Python file, so I'll put it up in Sublime. Okay, there we go. I'm going to have both the directions open and my quiz open while I go through these directions. So we'll take a look at what it's asking me to do. So let's read the directions. Okay, don't cheat. Use OK. That's how you test with OK. Great. Okay, so now we get to our first question. Is implement make change, which takes a positive integer amount and a dictionary of coins. The coins dictionary keys are positive integer denominations and its values are positive integer coin counts. Okay, so it looks like we have some sort of like piggy bank, right? So pennies, in this case we have 4 pennies and we have 5 nickels, right? Which is what it says right here. I'm sorry, 2 nickels. The make change function returns a list of coins that sum to amount. We pass an amount as an argument here, okay? With the count of any denomination k in the return value is at most coins k. Alright, okay, so it looks like what that's saying is here, if I only have like one 2 value coin, then I can only have one 2 value coin returned, right? Here, you know, ideally I would make change for 4 with 4 pennies so that I could keep using the smallest denomination, but I only have 2 pennies. Alright, so I have 2 pennies and then 1 2 coin. Okay, that's cool. So if there are multiple ways to make change for amount, prefer to use as many of the smallest coin available and place the smallest coins first in the return list. Alright, so what I'm going to do today is I'm going to pretty much just go through this quiz as though I had never looked at it before, and you can get an idea of how a TA would approach starting this quiz, you know, straight from scratch. So the first thing I would do is what I'm doing right now. I've pulled up the quiz in Sublime and I'm looking at it at the same time that I'm looking at these questions, right? So I want to make sure that I don't lose sight of what the question is actually asking. Hopefully you would have done this sort of the day before the quizzes do. We tend to give 2 days for quizzes, right? So you have a day to look over stuff and let it percolate, and then a day to actually start writing code. Okay, I would also have been calm. You know, you have to remember that many people have solved this before you, and it would also be okay if you don't solve it. It's only a few points. So deep breaths. We're gonna start the quiz. Should be super fun. Oh, shout out as well to Samantha and Josh for encouraging me to do this and for walking through it with me in office hours. You guys rock. Okay, so make change. So this looks a lot like something that we had in homework 3 to me. So this looks like we're given some amount and we're given some set of coins, and we have to make change and return. Well, first off, we also have to return whether or not you can make change, right? So here we're not able to make change with we're not able to make change of a value of 4 with only 1 2 coin. So we're going to return none. So I think in homework 3, we had a similar problem called count change. And in count change, what we had was a you know, instead of having some list of coins that we could choose from, we had we sort of had some like biggest coin that we were allowed to choose from. In this case, every biggest coin had to be a power of 2, right? So we're returning the number of ways to make change for amount. But really, we just want to, you know, this is ultimately just going down the recursion and returning a 1 if it's successful and a 0 if it's not, and we're adding them up together. And so here I can sort of see, okay, wow, this looks like something that I want to use recursion on. It sort of seems to me like a natural recursive candidate, especially since we give you something called rest, right? So whenever you see something called rest, or you see something where, you know, it looks like we're starting to break the problem down a little bit. So we have sort of some big problem where we're trying to make change for 2, or we're trying to make change for 4. If it looks like you're able to break the problem down into some smaller variation of that same problem, in this case, if I have make change for 4 and I use 1 penny, and I'm making change for 3, and I have 1 fewer penny remaining, right? So you can sort of see that like this looks like a natural candidate for recursion, right? So whenever I see this rest, I think, okay, well, this looks like it's going to be a recursive candidate. Now, what I would do here is I would sort of take out a piece of paper and I would try to draw the recursion that I saw for the problem that was similar. which before was this homework 3. And what you'll see when you do homework 3 is that you really have two choices, right? Either, in this case, so I'll walk you quickly through my code here. So first things first, what I do is I create the largest power of 2 that you're allowed to use. And I have some helper function here because you're not given really enough information with just amount. You need to keep track of the coin that you're using. So when I had this count change question, it sort of says count change for return the number of ways to make change for some amount. You pass in an amount. You also want to keep track of a coin. So I added a coin variable, which is why I made a helper function. And then here what I do is I define my base cases. The base cases are if I'm out of coins to use, or I've overshot my amount, so I've been passed in some negative amount, then this is not a valid way to make change for this amount. Otherwise, if I've exactly nailed my amount, so I've been passed in the amount of 0, then I can return 1. You know, I've won. There's only one way to make change for a 0 amount. Then in my recursion, and you should draw this out, because it's a little hard to see just from looking at my computer. In my recursion, I either decide to use the biggest coin that I have, which in this case is coin minus, so I have some amount, right? And I have the largest coin. The coin is going to be some large power of 2. And I can decide to either use that coin, which is what I'm doing here. So I'm using that coin to help make change for amount, and I keep track of that coin. Or I just forget about the coin. I say, well, this coin might mess me up later. Mess me up in sort of there's ways that I'm able to make coins later, so I'm going to forget about it here. And I'm going to see how could I make change if I decided to not use that coin. So seems like a natural way to approach this problem, this make change problem. And here we're given the smallest coin, so we know what coin we want to use. It was already decided for us, given a starter code. Then the rest, that looks like the place that we're going to keep using our recursion. So let's first start by sort of defining our base cases, right? Alright, so before we had a base case that was sort of amount equals 0. So that makes sense, right? So if I'm passed in something that, you know, if amount equals 0, so if I'm passed in, I'm trying to make change for 0, an amount of 0, and that's pretty trivial, right? All I have to do is return some empty list. And the reason I'm returning an empty list instead of none or instead of something else is that I always have to return an empty list if I'm able to successfully make coins, right? So I'm calling an empty list a successful coin production. Okay, so that's why I'm returning an empty list there. So the other option, one of the other options is defined already. So if not coins, which means I'm out of coins and I have no more coins, I have this empty dictionary, then I'm going to return none. So it looks like remove coins is defined here. What does it do? It's going to copy a dictionary. It's going to remove a dictionary, the item from the dictionary. Or it's going to decrement the item from the dictionary. And then it's going to return the copy of that. Then change machine we'll forget about. Okay, cool. And so this is amount equals 0. Return an empty list. And then if we don't have any coins, then we're going to return none. We weren't able to. No amount that we have, we're able to make change for if we don't have coins, except for the amount 0, so that's okay. Okay, right, so amount 0, amount equals 0, return an empty list. If amount's less than 0, though, we want to return none, right? So if we're passing some nonsensical less than 0 amount, then, you know, that we can't make change for that. It's sort of nonsensical. We should just return a failure. And this will become important. It's important to cover all your base cases. This is an important base case if we accidentally overshoot. So say the amount that I get is 1 and I only have a coin that's of value 2, then I'm going to overshoot. because I have no valid ways to make change for the value 1, given that I only have a single 2 coin. Okay. And we'll print some stuff out, and that might make some sense. Okay. So here I've defined some base cases, and yeah, maybe it makes sense to test that it works for these base cases. So what I'm going to do is I'm going to take this, I'm going to go into my quiz 2 folder, which is in documents, sorry about this, spring, TA, CD, whoops, CD quiz 2. Alright, okay. So first things first, I might want to do Python OK. Oops. Make sure I have Python 3 installed. Max Wolf. Uh-oh. Now you all know my email. Okay, so unable to complete backup, whatever. These tests are not useful for me, right? Right now I'm just sort of testing basic functionality. So what I want to do is I'm going to go python-i quiz2.py, right? Okay, so now I've loaded up this file into Python, and I'm able to sort of run through my doc tests as is. Alright, well this makes sense. I'm getting to the end of the file because I'm not hitting any of my base cases and I haven't defined my recursion yet. So let's see if I can make change for something that I want to make change for, right? So if I'm given just a single penny and I want to make change for 0, I expect this to return an empty list. Okay, perfect. That's exactly what it does. Now see, what if I don't have any coins left? Oh, okay, that's weird. This should return an empty list even if I don't have any coins, because I've successfully made change for 0. These two shouldn't be different, because I don't need any coins, right? So maybe that points to my base case not being in the right place. Okay, so my base case is amount equals 0. I think it makes sense for this to be up here, right? So I like to think of trying to put my success base cases at the top, because if you're successful, then you want to know when you're successful, right? You're going to be successful far less often than you'll fail. Most of the time, you're going to try and be making change for something that, you'll eventually get to the end of your recursion and it just won't work out. So we definitely want these successful recursive branches to bubble up. So okay, great. So return blank. So now let's exit this. I've reloaded the file into Python. Oh, that's not what I wanted to do. Make change for this. Okay, that's fine, but what if I make change for 0? Okay, good. Now if I get an empty list, okay, cool. Alright, so I'm expecting an empty dictionary to also return an empty list. This is what I get. That's great. Okay, so I feel pretty comfortable with these base cases. These feel like good base cases to me. So maybe let's start thinking about how we might do our recursive branches. So we looked a little bit at the homework, and the homework 3, where we had count change, it seemed like one of our recursive branches was sort of use coin, right? We wanted to actually use this coin. Oh, and the one reason I'm not defining some helper function here, which I think was sort of something that I saw occasionally in office hours, is because it looks like I already have enough information to do the recursion here, right? So there are two things I'm likely to be changing in my recursive steps. One are the coins that I'm allowed to use, right? So, after I use a coin, I shouldn't still be able to continue using that coin. And another one is, the other thing that I might want to change is the amount, right? So if I'm using a coin, I might want to actually decrement amount. So here it looks like I have enough information and I don't actually need a helper function to sort of finish this problem. If I didn't have coins, then it might make sense for me to define a helper function. Okay, so I've decided I'm going to use this coin. I'm going to use the smallest coin that I have. So let's have a make change. Let's do a recursive call on make change. And we said we're going to use the smallest coin, right? So I'm going to say that I'm going to use the smallest coin by decrementing amount. So I'm getting closer to my base case, which is amount equals 0, or amount is less than 0. And now I've decided I've used the coin, so I need to pass in rest as my coins, right? So rest is going to be a dictionary of coins that has one fewer coin in it. Okay, so I'm using this coin. That's one of my base cases, and let's go ahead and write our second base case. So the second base case is I forget the coin. So let's call this forget coin. I'm going to make change, and I'm not going to decrement it from smallest because I'm not using it. But I still want to use rest because I've decided I'm going to forget about using that coin. I'm not going to use that coin. Okay, so we have a forget coin. And this actually, you'll see this comes up sort of right here. So here we make a set of coins that's 2, 2. We have two value coins, 2 3 value coins, 3 4 value coins, and 1 5 value coin. And when we're trying to make change for 25, if we didn't forget about the second 2 here, if you want to draw it out yourself, it'll make it a little bit more clear. if we were to try and use both of our 2s in this list, which is what we're like preferring, right? We're trying to prefer the lowest value coins and using the lowest value coins as many times as we can. Then you'll end up, if you use 2 and then 2 and always use 2 and 2, then you'll end up making it's unsolvable. You actually can't return a correct change amount for 25, given that you've used this coin and then another 2 coin. Okay, that's just something to keep in mind. This is sort of the logic behind why we need to forget coins. Whenever we're looking at a single coin, there's only 2 options. We either use the coin or we don't use the coin. And if we don't use the coin, we want to forget about it and not use it, right? So not keep track of it. So this is what rest is doing as well. Just some background to figure out, what the logic behind having a use coin and a forget coin is. Okay. Alright, so use coin and forget coin should be 2 lists. Now, which one do we want to prefer? So if use coin is going to be the one that used the smallest coin, and so we always want to prefer the list that used the smallest coin. So let's see if this is not equal to none. Then what we'll do is we want to return a list. We've decided we have used the smallest coin, right? So we're going to use coin plus use coin. If we don't include the smallest, we don't actually build onto our recursion. So use coin is going to return the change list for whatever. It's going to return the change list for some decremented amount and some smaller set of coins. But we've decided we're going to use smallest, so we need to include this in our list that we're returning. Okay. So now we have another thing. If forget coin does not equal none, then we want to just return forget coin, right? And then otherwise we want to return none. So if use coin does not equal none means we successfully found a way to use our smallest coin. So we've called make change on amount and smallest, and it's done the whole recursion, a way to successfully use that smallest coin that we decided we were going to prefer. And so if this is not none, it means we've been successful. If it is none, then we failed. That left branch has sort of all failed. I encourage you to go home and draw the recursive tree for this. It'll probably make things a little bit more clear. And then otherwise we're going to see whether or not forget coin is successful. So our backup strategy was that we forgot about the coin and then continued to do our recursion without using that coin. So if use coin is unsuccessful, then we're going to check to see whether or not, we can call this an else if even, whether or not forget coin was successful, which means it didn't return none, and then we can return forget coin. It's important here that we use not equal to none instead of just if use coin, because it might return an empty list, and we don't want that recursion to sort of just say that we failed even though we didn't fail. Alright, so now I'm going to test it in OK. I'm going to test it actually in my -I. Oh, great. Okay, cool. So it's working for these base cases, or for these like sort of pretty easy stuff. Yeah, we're getting return 1. I'm just copy and pasting this stuff from the doc test, which is probably not the most efficient way to do this. So we've made some coin lists that we're going to say is like a big bank of coins. So now I'm making change for 4 coins. We can sort of look at what coins we used. So it looks like our left branch was what ended up being successful. So we have 2, 2. Let's put some, maybe we can put some print statements in here to figure out what we're at each stage. So I'm going to print as I start. Here I'm going to print the coins that I have. I'm going to print coins. So amount, and then I want to print coins. Just so it's clear to see what the recursion sort of looks like. Oh my gosh. Wow. It's a lot of stuff. Okay, so let's see what happens. So we started with an amount of 4, and we started with this many coins. And it looks like we took our left branch. Oh, well, this is interesting. We took our left branch and decremented our number of coins that we had by 2, right? Then we also forgot about that coin. So we have sort of two options, where you either can remember that coin and use it, or forget about the coin and keep going. This is the entire right side of the branch of forgetting about some coin, right? Forget about the coin, forget about the coin, forget about the coin. Oh, you know what? Interesting. Okay, so I know what's happening here. The reason that we don't see this is because we don't print. Yeah. So the reason we're seeing this whole tree is because I've actually put this forget coin. I'm doing the whole recursive tree either way, and it might be easier for me not to do that. It's going to be a little bit more efficient for me to only calculate the right side of the coin if I need, or the right side of the recursion if I need the right side of the recursion. So you see here, I can see that I've taken the left side of the recursion and started that. And actually I think I've finished it in this one. And then what I do is I follow the whole right side of the recursion, and I keep forgetting about coins, right? So I'm going to forget about all these coins. It's going to hit base cases all the way down. And then I can fix that just by moving this right base case, or this right recursive call, behind my successful recursive call. So I'm going to, if my left branch is successful, I can just return out and I don't need to calculate my right branch. So it's interesting how important, how tremendously important having the base cases in the right order is, and having the recursive calls in the right order as well is. So if you're having trouble, and if you were having trouble, you might have noticed that it might make sense for you to look back at your code and figure out whether or not you had this successful base case at the front, whether or not you had it somewhere down here. Okay. Well, so I think I'm pretty confident in this. So let's go ahead and test it with OK. Okay. Well, it looks like the only thing I'm failing now are these change machine things. Okay, which makes sense because I haven't implemented it yet. All right. If people have questions about this, sorry I was so rambling. If people have questions about this, feel free to post a comment or come to office hours. Hopefully this made the make change question a little bit more straightforward. And sort of see, I had my 2 recursive calls. I either use the coin or forget about the coin, and then I made sure to be super careful about my base cases, right? Covering all your bases for your base cases is really important. Just going to put these together to make that a little bit more clear. Okay, cool. Saving all the time in case something tremendously awful happens. Okay, so now I have a change machine. So let's look at the question. Let's pull them up together. I've successfully implemented make change. Great. I can use the remove one function in my implementation. Blah, blah, blah. Hint, using the smallest coin to make change. It turns out there is no way to make change using the smallest coin. Okay, so they give us a hint as to the recursion, right, which I didn't see that before. Simplest solution does not involve defining any local functions, but you can define additional functions if they wish. So we're trying to steer you away from using any helper functions. Okay. Right, so now we want to complete the change method. Okay, it's a method, we're doing object-oriented, of the change machine class. The change machine instance holds some coins, which are initially all pennies. Started with a bunch of coins. The change method takes a positive integer coin, adds that coin to coins, and returns a list of that sums to coin. The machine prefers to return as many of the smallest coins as possible. Alright, great, so this is literally exactly like make change. Order from smallest to largest. The coins returned by change are removed from the machine's coins. Oh, this is pretty much just implementing make change, given that we're doing this make change for object-oriented stuff. All right, that's fine. Okay, so let's look at what. Oh no, daylight savings time. Okay, so M coins. We start with some coins. M change. Blah blah blah. 10 pennies. Alright, so yeah, it always makes sense to read the doc tests first to figure out if you know exactly what is actually happening. So let's start up here. Oh. So I start with 2 pennies. That's what this is doing. Making change for this, I want to use both of my pennies. Oh, interesting. So now when I say make change for 2, I'm actually inserting that coin into 2. So that's sort of cool. So I'm inserting that coin before I do any of my make change calculations. And then make change 3, and it just returns 3. Oh, so this is returning 3 because we can't make change with the coins that we had previously in our machine, and so we need to use the coin that we just return the coin that we were passed in. So no one loses money on this coin machine. Okay, so I think I'm ready to start this. Hint, call the make change function in order to compute the result of change, but update self.coins before returning that result. Okay, so we get a sort of a nice hint. You can use make change. Well, that's good to know. Alright, so first things first, it looks like, just from this implementation up here, looking at my doc tests, that I need to first insert whatever coin I have into my self.coins. So the way I'm going to do that is with dictionaries, I remember that they're mutable, but I'm going to get a key error if I try and key into something. So if I try doing something like self.coins, try and make this more in the middle. If I do self.coins coin plus equals 1, this is going to give me a key error if this coin doesn't exist, right? Because I'm trying to increment a value in my dictionary that doesn't have any keys. There's no key for coins yet if I haven't actually put a coin of that value in before. So I'm going to do this check, and this is a little janky, but we'll see what happens. If self.coins, if coin in self.coins, then what I want to do is self.coins coin plus equals 1. Else I know that I haven't seen coin before because it wasn't a key in my dictionary, so I can do self.coins coin equals 1. Okay. So those are my two options. I want to start by instantiating self.coins to be what it's supposed to be. It's supposed to be something that has this extra coin in it. And that way I'm guaranteed to always be able to return the right number of change with make change. Alright, so make change works. So let's print what. Let's do the following. Let's just say change list, because we're going to get a list of coins back out. So let's do change list is equal to make change. And then what did make change take? Make change took an amount and some dictionary of coins. So let's say we're asked to return coin amount, so just some number. And we want to use the self.coins dictionary as our dictionary of coins, because we're pulling from the coins that the machine has in it, right? Alright, so let's just print this, because I don't really know what this is going to look like. We want to make sure that this is like actually returning the right number, the right sort of coins. Okay, so let's see. So we have. So I need to make a change machine. Let's see that this is true. This should be true because this is not something we wrote. Okay, good. Confirming that the GSIs didn't miswrite something. Alright, great. Alright, so this is just printing it out there, right? We're just printing out what coins is returning. Oh, now this will be interesting. Let's see whether or not. No, it's not true. Alright, so let's figure out what m.coins is. Oh, okay, so we haven't yet. Oh, that makes sense. We haven't yet taken out from our. We haven't removed from our self.coins the coins that we actually used when we made this change list. So now we need to actually modify self.coins. So what are we going to do for that? Well, we're going to remove one coin for each of our coins that we actually returned in change list. So let's do that. It looks like we've already gotten a function called remove one. I hope this works. So for coin in change list, let's just remove one. What does remove one take? It takes coins and coins, so we're going to remove one, self.coins, coin. Let's print coin. Make sure I'm actually removing all of the coins that I think I'm doing. And let's, for good measure, print self.coins. Okay, I'm going to exit this. And now, I'm going to do the following, copy and paste all this. Oops, whatever, m.coins. Let's just see what it looks like. Makes sense, m.change to, so we've printed stuff out. So this is the coin that we're moving, and then this is self.coins before we've removed anything. Fine, coin removing. Oh wait, what? Shoot, we haven't removed anything from self.coins. So what's wrong here? Remove one self.coins. Remove one self.coins creates a copy. Okay, so well that's good. So I need to make sure that I'm reassigning self.coins to whatever this remove one self.coins is, because it's going to make a copy of the dictionary and then modify that dictionary. So it's not actually modifying our self.coins. So now let's try that again. Python, I want to do change machine, so I'm making my change machine. Now m.coins, cool, so I'm starting it out, m.change, and let's have a change 2. Oh wait, so it's not changing here. Self.coins equals remove 1. So. Well, let's just see what m.coins is equal to now. Oh no, so it didn't modify it. Interesting. Remove 1, self.coins coin. Okay, well, so we have this, remove 1 coin. For coin in change list, we're going to print the coin. We want to remove 1 coins. Am I saving this? Let's print what remove 1 coins is equal to. Okay, and so we've run into a little bit of a snag, but this should be fine. This is what happens in an actual quiz. Change machine to m.coins, m.change to. Oh, maybe I just didn't save it. That's okay. Well, that makes sense. So now let's get rid of these print statements. So I can see actually that I am modifying now my self.coins, right? In this next iteration, self.coins is equal to 1. This is only 1 penny, right? So what I'm doing is if I'm going to return a set of coins, right, I need to make sure I remove them from my bank because I don't have them in my bank anymore. Okay, great. So we're done with this. Or bank is equal to coins in this case. All right, great. So now let's just return change list, which is what we wanted to do. We've tested that. Let's see whether or not this works for m equals change machine to. No, I put a dot there. m.coins, m.change to. Alright, great. So this is what we're expecting as return. Let's save this. Let's exit this. Let's check whether or not Python's okay. We're successful here. Hey, I got 100%. Alright. Okay. So here, just a quick overview of what I'm doing. I'm making sure that I put my coin into my coins list. I can use my make change, which I just wrote to create a list of coins that I want to use, and then for every coin in that list that I'm returning, I need to make sure I remove it from my piggy bank, right, because I'm not using it anymore. And then we can just return change list. Okay, hopefully this was helpful for people. Sorry it was a little rambly. I'm sort of literally just going through it as though I was going through it in front of you. If you have any questions or comments about it, feel free to leave a comment on YouTube or on Piazza, and I'll be sure to answer them. Okay, great, thanks for watching. Bye.